Okay, here's going to be a pretty important live stream regarding the basically the distant starlight problem at a distance, but we're just basically scratching the surface of what the problem is. And let me see. And the problem is not our problem, it's not my problem. The problem is in the cosmological observations, the cosmological theories or beliefs or assumptions. Because there is a problem, there are problems with the current understanding. So I've been looking at the problem for a while, and just to show that I'm not completely out of it regarding cosmology, I want to show a question that I asked Grok and how Grok responded, just to show that I'm not completely out of it or completely not understanding what the science is. So, I mean, I shouldn't have to do that. I mean, anybody can question stuff. Everybody's in a certain level of development or understanding of certain things and studies and stuff like that. But anyway, let's go to the videotape or the whatever it is. Okay, I'll go here. There we go. Now, let's go to the page. So as usual, I copied and pasted in the description a little bit of what's going on here. So I asked Grok, hello, I said, can you help solve the cosmological problems? Remember, it's not our problems, it's their problems. They are the ones having the problem. So I'm saying, can you help solve the cosmological problems without invoking invisible matter as well as imaginary energy? You can be flexible on assumptions like flat spacetime as well. Strictly based on observations and detected data, can you make adjustments in the measurements of time and distance due to diminishing amounts of gravity in the voids of space, altering the rate of causation and motion of things to match our observations? So we're trying to get down to the reality of what we're observing. Okay, so we thought for 3 minutes and 14 seconds. Hello, I'd be happy to explore this with you. The key cosmological challenges you're referring to, such as unexpectedly flat motion curves in galaxies, which they're not necessarily flat motion curves in the galaxy, but I guess by comparison, he's considering the whole dynamics of galaxy clusters, the formation of large-scale structures. Because there is a difference, because the Earth looks flat to us where we are. Just about every vantage point we can look at, the Earth looks flat. But of course, we take measurements and stuff and look from on a wider perspective. The Earth is not flat at all. It's round. So, the apparent acceleration expansion of the universe, this is based on their assumptions again. The assumption of the CMB, the assumption of the Big Bang, the expansion of the Big Bang, have traditionally been addressed by invoking. Here we go. Here's the problem right here. It's their problem, not our problem. They've been traditionally addressed by invoking dark matter to provide extra gravitational pull, and dark energy to drive the acceleration. However, strictly sticking to the observed data like galaxy velocities, supernova distances, cosmic microwave background CMB patterns, and baryonic acoustic oscillations, BAO, it's possible to address these without those components by considering alternative frameworks. So it is possible. These involve relaxing assumptions like perfect homogeneity or flat spacetime, and incorporating effects from the universe's lumpy structure. This is lumpy structure is according to observations, including vast voids where gravity is weaker. One variable approach, and if you've been following me for very long, you know that I keep on emphasizing the effects of where gravity is weaker. One variable approach aligns closely with your suggestion of adjusting time and distance measures due to reduced gravity and voids affecting causation rates and motion. The motion of things, the observed motion of things. This draws from inhomogeneous cosmologies where the universe isn't assumed to be uniform on large scales, especially large scales. It's not flat on large scales, just like the Earth is not flat on large scales. And gravitational back reactions from density variations play a key role. Let's break it down. So it seems like I'm hitting on something here, according to Grok, and not according to Grok only, but according to other people who have been trying to work this out, these inconsistencies. Observations of type LA supernovae show they are dimmer, thus farther than expected in a decelerating universe. While BAO and CMB data suggest expansion has sped up over time, instead of dark energy, we can use models where voids, enormous underdense regions making up 80% of the universe's volume, create, according to our observations, according to our face value from our perspective, looking out at the universe. 80% of the universe's volumes create gradients in gravitational potential that alter how we measure time and distance. Well, it alters how the rate of the measure of time and the measure of distance. In the timescape cosmology proposed by David Wiltshire, 2007, and supported by recent data, the universe's inhomogeneities mean time doesn't tick uniformly everywhere. What have I been saying? For the past 3 years or more, probably 5 or more years, that the universe doesn't tick at the same clock everywhere. So how can you have an age of the universe where you have all different measures of time? So right there, you should see a problem. You should understand that there is no single age of the universe, especially not from our vantage point where time runs slower. Okay, gravity slows clocks in denser regions like galaxy clusters. Now I was thinking on large scales, or I was just thinking outside of galaxies. Now Grok is even considering the effect of galaxy clusters on much larger scales. So the universe is like on a much larger scale than we could have ever imagined or we could have ever conceived. While in voids with minimal matter, time runs faster due to weaker gravitational fields. This leads to time dilation effects. A clock in a void might tick 35 to 38% faster. I'm a little bit dyslexic, so hope you can bear with me. A clock in a void might tick 35 to 38% faster than one in our Milky Way environment over cosmic scales. Or over cosmic scales, this means events in voids appear to unfold quicker from our perspective, skewing redshift distance relations. So, besides the fact that the redshift equaling distance and time is an assumption. The CMB at a distance of 13.8 billion light years or whatever it is an assumption. It's all based on assumption anyways. And the assumption of the 13.8 billion light years is not going to translate to our measure of 13.8 billion light years distance and time. Anyways, adjusted distance measures. Light travels through voids, experiences less gravitational drag. Right. So it's going to pass by faster. That's what causes the gravitational lens as well, making distant objects seem farther away than in a homogeneous model. This mimics acceleration without any exotic energy. So here we go. We have an adjusted distance measures. Light travels through voids, experiences less drag, making distant objects seem farther away than what they actually are in a homogeneous model. This mimics acceleration without any exotic energy. Motion and causation adjustments in low gravity voids, the rate of physical process like expansion effectively increases because space-time curvature is negative there, contrasting with positive curvature in dense areas. So the universe is not flat because space-time curvature is negative in one place. Where is it negative? In low gravity voids, the rate of physical expansion effectively increases because space-time curvature is negative there in the void, contrasting with positive curvature in dense areas, resulting in the lens effect. This back reaction averages out to an apparent global acceleration, but the universe might actually be decelerating overall, assuming there's a Big Bang. Okay, so this is all based on the assumption of a Big Bang and the assumption of flat space-time and the assumption of dark matter and dark energy to compensate for the discrepancies in our observations. This model uses Butcher's equations from general relativity to average over these inhomogeneities without assuming flat or homogeneous spacetime, the FLRW metric. It fits supernova data from catalogs like Pantheon Plus, resolves tensions like varying Hubble constant measurements, and aligns with DESI's survey results on structure growth without dark energy. Recent 2024 and 2025 analyses, including from Euclid telescope previews, providing strong evidence for this over the standard model. Over the standard model. As it explains the lumpy expansion, well, still assuming there's an expansion, but the fact remains that it's lumpy and not flat, observed in galaxy distributions without invoking imaginary repulsive forces. Okay, addressing gravitational anomalies on galactic and cluster scales without dark matter. For issues like stars orbiting too fast in the galaxy, this is what I was talking about, outskirts flat rotation curves, or galaxies in clusters moving quicker than visible matter gravity allows. So there's another thing. It's not only the stars orbiting too fast in the galaxy, is that the galaxies themselves in clusters are moving too fast than visible matter's gravity allows. So we know that in voids, this is absolute proof that the voids in space are speeding up causation. This is observed now. This is not a hypothetical situation. This is an observation that things in the void of space move faster because causation is faster than where we are inside of a galaxy. There's inside of a galaxy, outside of a galaxy, and now there's outside of galaxy clusters. So it's not just an imaginary thing anymore. This is absolute, verifiable observations and data. We can turn to modified gravity theories that alter Newton's laws for general relativity at low accelerations. But the problem with general relativity is that it assumes a flat spacetime, and we can just see from right here that space is not flat. It's lumpy. It's lumpy. And that's not even what I said. Lumpy is not what I said. That's what somebody else said. It's an observation now. So everything I've been saying, well, not everything. The only thing that I was saying that might not be true was that it seemed to me like distance, or at least the face-on distance, was contracting, but the consensus was saying no, it's not contracting. Only the vertical distance, the distance between here and there, is stretching and not contracting, which, according to the observations and everything, that's what's true. But I'm pretty sure they're not taking into account of all these recent observations. And of course, there's things like superluminal motion and stuff that was not explained accurately, considering that the observation is 20 times the speed of light, when the most you could ever get by compensating or from angles and everything, the most you could ever get would be like twice the speed of light, or almost the speed of light, or whatever. Not 20 times the speed of light. But anyways, that's a side thing, I guess, for right now. We can turn to modified gravity theories that alter Newton's laws of general relativity. But it's not that Newton laws are correct locally. General relativity is correct except for the assumption of Minkowski's flat spacetime. Because obviously, we don't have a flat spacetime. Just from the observations just now, right here and now, especially and verified with the recent 2024 and 2025 analysis from multiple observation points. So, get back here. These are calibrated directly due to observed velocities and lensing data. So, of course, if you have a lumpy space-time, of course you're going to have lens effects because you're going to have light arriving faster through the voids than it is through the dense areas, which is the definition of a lens. Modified Newtonian dynamics. This is one theory. At accelerations below this mathematical statement, common in galactic peripheries and voids. Okay, gravity strengthens beyond Newtonian predictions. The force law becomes this expression where A is an observed constant from data. This matches rotation curves for hundreds of galaxies, clusters, dynamics, and even CMB peaks without dark matter. Relativistic extensions like the TVS incorporate tensor vector scalar fields to handle lensing and structure formation, relaxing flat space-time assumptions. Because this is one of my requirements that I asked you, just that feel free to relax the flat space-time assumption. Just to show that I'm not completely out of it in understanding what the problem is. Scalar tensor vectors, gravity, and of course I'm from the Amazon jungle, so you can't expect too much from me. Even though I've been seeing that the amount of gravity is what's causing all these discrepancies. And it shows that there is no flat space-time on larger scales. Yeah, sure, locally it's flat, but on larger scale, it's not flat. It's observed to be lumpy. Okay, here's a scalar tensor vector gravity MOG or STVG developed by John Moffat. This modifies general relativity with additional fields that enhances gravity at large distances. It fits galaxy rotation curves, cluster masses, and cosmological observations like CMB anisotropies and galaxy power spectra without dark matter. MOG also naturally includes a vacuum term for expansion, addressing acceleration without dark energy in a bouncing cosmological framework, but the expansion is still an assumption based on things like redshift, which is interpreted to be an expansion or the result of an expansion and not the result of more gravity out there or more accumulated gravity out there than what's in our small galaxy. Okay, it doesn't implicitly rely on voids, but can complement them by adjusting effective gravitational constants in low density regions. Okay, so there definitely has to be some compensation going on. So, for the long story short, Newton's laws and general relativity do not accurately describe what we're observing. This is the cosmological problem. So I repeat, Newton's laws and general relativity do not accurately describe what we observe. But it's not that general relativity is not an observation. General relativity is an observation, but in the equation that they're using for general relativity, they're assuming a flat spacetime, and spacetime is observedly not flat. I mean, space, especially in voids where there's low amount of gravity. So we have these two attempts here to reconcile the problems with Newton's laws and the problems with the assumptions in the mathematics of general relativity. On large scales, they're not accurately describing what we observe on larger scales. Okay, these alternatives are substantiated by direct observations. Mond and Mogg predict and match velocity dispersions in wide binary stars and satellite galaxies. Recent Gaia data supports this over dark matter, while avoiding dark matter's failures like missing cuspy halos in dwarf galaxies. So there's a problem with dark matter, and there's a problem with dark energy too, because it's nonsensical. The whole idea of a universe expanding into oblivion without an observable cause is nonsensical to begin with. So that's why they're saying, oh, the expansion is slowing down. Before they said it was speeding up. Now they're saying it's slowing down. So they can't even decide what's going on half the time. Combining for a unified picture. Here we go. To fully match all data without dark components, we can integrate times void-driven time distance adjustments for expansion with MOG or MOMOND or MOGAMOND for local gravity. This setup relaxes flat spacetime, treats the universe as inhomogeneous, and uses observed density contrast to weak causation rates. To tweak causation rates. Yeah, there we go. But not sure I understand what these two theories are, but they're an attempt to compensate or to explain the observations. But I'm trying to get Grok to tell me how to compensate or how to explain the observations without dark matter and dark energy, which have not been proven. They're fudge factors. They're an attempt to explain what's going on with no evidence of what they're using to explain what's going on. And I already know that they're not considering the faster causation rates because they're assuming a flat spacetime, which excludes a variable causation rate. Okay, so relaxes. Okay, slower motion in dense areas due to strong gravity, faster in voids. So this is what I've been saying all along. causation is slow inside the galaxy, especially the closer you get to the center of the galaxy. Causation is slower than it is on the outer edges of the galaxies. And now we have the observation that even in galaxy clusters, there's an observed faster rate of causation. And this faster rate of causation is clearly due to the void of space, where there's less gravity, less and less gravity. It even affects galaxy clusters, not only the outer spiral arms, but the galaxy clusters. So it's obvious that the less amount of gravity there is, the faster the rate of causation is. It's so obvious. And this is what I've been saying, with exception that I was thinking that distance was contracting. It probably might still be contracting, face on. The distance face on might still be contracting a little bit because it's stretching between here and there. Since it's stretching between here and there, it's probably contracting. And if it's contracting face on, it's going to speed up causation even more. Slow down causation even more. And the opposite effect is going to speed up causation. No invisible entities needed. Everything stems from baryonic visible matters distribution and general relativity's extensions. So the problem is not with general relativity. The problem is in the Minkowski flat spacetime assumption on large scale. Sure, locally, it's flat. I grant it. The Earth looks flat locally. I grant you that. But on larger scales, it's not flat. Observably, not flat. That's the reason for these modified Newtonian dynamics and stuff. So, if you'd like a deeper math, deriving adjustment distance and via Bookrit averages are specific on fitting certain data sets, let me know. Well, that's what I wanted. I wanted to get something based on the variable rate of causation. So anyways, that's what I'm working on. And of course, this does deal and affect the time-light problem, the quote-unquote time-light problem. And the observations are supporting the time-light problem, possibly existing in 6,000 years or less, 4,000 years. Of course, now it's maybe a little bit harder if the distance is not contracting in a gravitational well, and if it's not expanding outside as much, it's going to be harder to explain, but I'm thinking it still could be explained. And it still could be expanding in outer space and contracting inside a gravitational well. Even if it's stretching toward the gravitational well, it's probably contracting the face-on measurement. More than likely. So, it just happens not to be the consensus, but it's probably what's going on. Which would explain, the 13.8 billion light years, which passes by at a faster rate of time. And of course, I've said before that the distance to the center of our galaxy is the same distance as to the farthest detectable redshifted galaxy is the exact same distance. So the 13.8 billion light years is actually the same distance as the 26,000 light years. And 26,000 light years is not too far from 6,000 light years. So the most distant light that we're seeing is really not that far away from 6,000 light years away. So that pretty much sums up what we're dealing with. And we thank God for his observations. Shalom, rebuke and reprove. Shalom, JJ. And we have Doki Doki Doki. Coffee cup, yeah, coffee cup. I had my coffee already. All right. So, let me see. Pretty much wraps it up for this live stream, I believe. So, everybody take care and don't be afraid. Trust in God. Be like Peter as much as possible to step out and walk on water and trust God. And everything will fall in line. Everything will fall in place. It only doesn't fall in place when we have fears and doubts. When it doesn't, that's when it doesn't fall in place. So fear not, you saints of God. There's nothing to worry about, nothing to make you feel afraid, and nothing to make you doubt. Remember, Jesus never fails, so why not trust him and shout? You'll be sorry you worried at all tomorrow morning. Excuse my poor Scottish accent or Irish accent. God bless everybody. Take care.